Hey, as we're starting to cover topics relating to compilers and a little bit of software optimization in this course, I thought I'd introduce a tool that I found very helpful to understand that connection between C programming and the underlying ISA and specifically MIPS for this class. So there's a lot of ways you could do it. The general name for a tool that allows you to go from source code down to your machine code for your native machine is referred to as a compiler, right? But oftentimes we want to compiler for an architecture that's not the one that we're actually currently running our software on. And that's referred to as a cross compiler. And it's very common in the context of, say, embedded systems where your actual target device is this low powered, tiny little embedded thing, and you still want to compile code for it. And in your previous classes that do compile for embedded systems, you would be actually using a cross compiler and maybe just not using that term. So that's always one approach. You can always install your own cross compiler. There's many packages for doing so. I like this one website that lets you really explore different compiler installations to see what they can possibly do for a particular architecture. This is godbolt.org. I thought at one point that was just a very cool piece of branding, but in fact, that's just someone's name. And it's the Compiler Explorer website that if you haven't run into before, well, today's your lucky day. It lets you select from various input languages on the left tab here, and where you actually enter your code. And then it runs in a backend where it auto-generates the assembly output for a particular compiler and a particular architecture. Originally, it was designed as a way to explore, how different compilers approach different optimizations, and we can still use it for that purpose. It also has targets for different backends. So if you look at the list of architectures that's supported, there's a decent number, but particular, for example, for your native 64-bit x86 architecture, you can play around with every version of GCC that's ever been released and see, how they generate code in different ways. Compilers are pretty complicated pieces of software. And in this semester, we are the compiler, and we really can't hope to compare what we do to what a modern compiler is able to do in terms of code generation, in terms of optimization. It's a pretty fun website to play around with to see, what kind of optimizations our compiler is able to do in this day and age. This is just an example I like to show what's possible. The code example on here is just running some silly little function to determine if we iterate through a value. We check to see as x is 0, less than num. If that value is odd, add it to that value. So it's squaring some odd values as it iterates through an array. And this website's pretty cool because as it generates the code, in this case I selected the x86-64 GCC 6.2, as well as some basic optimization flags past the compiler. And we don't need to go into too much of that detail for now. It actually does that highlighting to show you the equivalent of, for our line of C code on the left here, what the equivalent assembly block would correspond to. And this is Intel assembly, so this should look a little ugly, and it does, right? Intel is famous for, in this case, for the SSE instruction set, all sorts of really crazy instruction mnemonics that you have to have the data sheet in front of you to know what they're all doing. But it is pretty cool to see that, from here, you get this assembly output, and you can see that one-to-one connection between what's happening in your C code and what's happening in your underlying assembly. It also, as I mentioned, can be used to show sort of the power of optimizations in compilers. In this case, although this seems like a very trivial change, if I get rid of that bang operator there that basically inverts the condition, I'm now checking to see if it's actually odd as opposed to even. Since it starts at 0 at plus is equal to 2, the compiler and its optimization path is actually smart enough to look at this entire block of C code now with a for loop that executes and an if statement that's never taken. And it's not that important why it's not taken, but it's always even, and it's checking if it's odd now in this code. It's smart enough to recognize that, and it's actually smart enough to eliminate all the code that it's emitting, and instead just returning 0, and that's what's happening in this assembly code that we have here. XOR the value with itself and return 0. So that's Compiler Explorer in general. It's great for playing around with different optimizations. It's great for looking at different compilers and how they generate code. For our purposes, we really want to care about the MIPS version of the compiler that's supported here. Again, you can always install your own cross-compiler, but this website already exists and does that for you. And this is sort of one of the default examples that I just slightly tweaked when you select C code here. So here I'm saying for my C code on the left, sort of arbitrary code just to show what our branches look like, right? If n is greater than 0, return num plus num. Otherwise, return num plus 7, where num is some input integers. And now when we look at the assembly code on the right as targeting MIPS, it should look a lot more similar, right? We should be able to look at that and say, okay, that looks kind of like what we have been doing in this class. And I think it's a perfectly fair question to have start raising your mind is, well, why are we going through all this effort of generating our own assembly code in this class, right? The compiler works, it gives us a result and we should be done and we shouldn't have to do this at all. How about for homework? Why can't I just plug the code that you're asking for in the homework or an exam, right, into this tool and call it done? There's a couple reasons why. First off, there's many variants of the MIPS ISA, and if we don't pass the exact right compiler options to the MIPS GCC compiler, you're going to get something that isn't quite right for what we are supporting. There's also some quirks with Mars that GCC isn't aware of, and so this code copy-pasted will not work directly. And I think from a academic integrity perspective, it'll be pretty obvious when you have auto-generated code. Compilers emit code that do not look like human-written assembly. Maybe there was a time when they did, but certainly they are either applying optimizations or just structuring things in a certain way that makes sense really only to compiler developers, and it's pretty clear that isn't something that you necessarily would have written yourself. So it's a good tool to confirm what you're doing, but it's not a free cheat code for the class. I mean, you could try, and ultimately, right, our goal in this class is to give you that understanding of that abstraction from C to ISA to microarchitecture. And if by the end of the semester you can go from this C code and understand exactly what's happening in this assembly, well, then we've succeeded, right? And that's fine. So you may not be ready yet to just take this and blindly make the changes needed for this to look more human readable. But as you gain an understanding of this, and if eventually all 27 lines of this assembly make perfect sense to you, then we've had a successful semester, and I'm happy with that outcome. So we can take a look at this code and try to import it into Mars just to get an example of a couple of the, I called them foibles, a couple of the headaches you would have if you tried to do that directly. Here we have Mars open, and I'm just going to throw that in there. And at first glance, I look at this and everything looks okay. But let's see what happens when we try to actually compile it. Only one error. That's not bad. The code was really simple. You can get a lot of errors if you're not careful. Error in yada yada yada, line 26, column 17, register 31, operand is of incorrect type. And I don't know who's wrong here. I said earlier that if Mars tells you something is wrong, we have to listen to Mars because that's the only tool we're using to simulate stuff. So Mars is telling me it's wrong. It's because it thinks the instruction has to always be called jump register, and that's fine. So as long as I change that jump to a jump register, it should be okay. And it did assemble. That's where you see now sort of the binary layout of the assembled instructions here. I want to see if there's any examples of so-called pseudo instructions, and in this example I don't see terribly many. Here's one example of a pseudo instruction, this move instruction. The first two shouldn't be. So if we look at the third instruction here, and that's a so-called move instruction, that's what we were referring to when we were talking about in class these pseudo instructions. They're there to help you as an assembly programmer be slightly more effective. Move is a very natural thing you would want to do in your assembly programming. Move from one register to the other. Not so dissimilar from a load store, except it's just from register to register. It's not a native instruction in MIPS. So architecturally, there's nothing you would implement to get a register to move from one place to another via a single instruction. Unlike some of the branch examples we were talking about in class, where it's not really clear whether more branches or fewer branches is the right decision, for this one, for a simple move instruction, there's really no need for it. We can implement a move via adding 0 to the register and storing the result in a different register. And that's actually exactly what's happening here, right? It claims it's a move instruction here as the actual assembly code we have, but the actual instruction it gets assembled down to, and MIPS is really great about this, is an add U instruction that takes the register we wanted to move, adds 0 to it, and stores the result in the destination register that we wanted to move things to. So this whole flow kind of works. You have to sort of see the connections between compiler output, Mars tweaks that may need to be made, and underlying pseudo to native assembly instruction encoding. For some of these pseudo instructions, it would be a greater number of static instructions than when we were just doing native instructions. Just briefly, in the interest of time, going back to the Compiler Explorer, I have another example here that is attempting to just do some matrix multiplication. And in my attempt to generate code that is the most 381 MIPS-like that I am capable of, for a much more complicated example here, here are the optimization flags I was selecting. Target for your target architecture, MIPS 32, revision 2. Of course, let me know about any warnings. Have a lot of context in the assembly. And this is something that we'll waste a lot of time on later in the semester. So that would be necessary for your code to operate correctly. And so for this matrix multiplication example, you can see it's actually generating quite a bit of code to be able to generate all of that, to generate the equivalent code for doing that inner loop, for example. It's all the same array arithmetic we were talking about. We should be able to optimize it further until, try a little bit harder. And it seems to be able to when we have that here. We can start with either example, but let's do the optimized example and see what happens when we try to compile this, assemble this in our Mars. Well, there's one gotcha already I can notice that, in our C code, we have this data region, but the Compiler Explorer isn't actually emitting that data region. That may be some option somewhere that I'm not familiar with, but for this, we should be able to figure out what the data region would need to be. So if this entire region is our assembly region in our, I lost my cursor here, in my Mars, we would also then have to specify where we would want there to be data region. So we would want to specify separately that there's text, basically our instruction memory region, and then .data, that is our data memory, where we need things to be stored in memory so that they have addresses associated with them. And we should be able to do A is a data type, and it was defined as an n by n array, where n is hard-coded to be 200 in this case here. So we would need 40,000 integers. We don't want to type 40,000 things in, no doubt. So instead of specifying it as a word or something, we can just say size. It would be, what did we say, 40,000 integers, so 160,000 bytes, and the same for B and C. That's a lot of memory. Mars maybe can't handle that much memory. We'll find out here in just a moment. So then we try to assemble this, and it's unhappy about, and maybe this .size directive, Mars does not recognize it. So, well, let's see what that corresponds to then. I refuse to look in the documentation while going live here, but Mars is complaining about .size. Let's see what it will allow us. A, we can certainly say A is like a .word. So it's not .size. Maybe it should be, but it's .space. Number of bytes that we need. I feel like .size makes more sense, but I didn't write this tool. Okay. Okay, so now we've allocated that. So that's at least the first compiler error that we have there. And adding an actual space after the word space would help. So then it's complaining about those load upper immediate instructions. This is definitely an example of, the compiler is generating something, but it's very clearly compiler generated code here. That actually doesn't correspond to our textbook MIPS, load upper immediate, given the high register associated with that address. The correct way we would do this in this class would be to replace those load upper immediates with load address instructions. let's see if we get past the first error there. I won't do all of this if that's the case. So line 12. So yeah, so for all those, it's complaining about the compiler generating something that doesn't correspond to our textbook MIPS. That's load address. Then we have load upper immediate, where it's adding that value into 14. We couldn't do that anyway. So that's not allowable in our textbook MIPS. Instead, we could just take the value we previously loaded as 9 and add that next offset to it. This one can then become load A of the value of B. Then one more, add UI of that 13 now becomes, add an 800 to it. That load immediate is fine. So this is loading into 9. Well, none of these would be necessary. None of those would be necessary. Anything else we have to get rid of here? Let's see if it compiles now. Add. You guys are supposed to catch me when I make these typo mistakes. Instead of add UI, it's add IU. Add immediate, unsigned. So add immediate, unsigned without overflow. And then the final error is the same one we had before. There's some disagreement between the GCC developers, apparently, and Mars developers, whether we can do a jump to a register or if it has to be a jump register. As I said, again, every time we have a discrepancy, we trust Mars, and Mars tells us we need it, so we're going to add it there. And then that actually does seem to work. And the final point I'll make is what can be very useful is we already talked about the pseudo instruction expansion here. So all of those LA instructions that we had here are in fact valid pseudo instructions, and they're getting expanded into those 2 instructions, and those 2 instructions would be a load upper immediate, which is a pretty straightforward one to implement, followed by an OR immediate. So it's a single instruction that allows us to load, in this case, a 32-bit address, and below it's load immediate for loading a 32-bit immediate. But for reasons we've been talking about in the class, you can't really fit that 32-bit immediate inside a single 32-bit instruction. There'd be no room for anything else. So load address and load immediate are very useful pseudo instructions, and they get expanded out into a 2-part instruction. You could do it other ways. You could do it with shifts and adds and things like that, but this is the way that Mars assembles that down into a load upper immediate followed by an OR immediate. And the final point I would want to show would be to test out that comparison between branch instructions that point to a label and then the actual branch encoding that happens. There's several examples in this code base, and there was one in the earlier code base that we can go back to because it's a simpler example. The example here that was just where we only had to change one thing, so we can go back to it pretty quickly. My Mars is acting up, so I don't know if I can grab it. There we go. So for this example that doesn't have all that stuff going on, because that's a lot to fathom, the actual branch instruction that's branching to L3, another way to think about branching to L3, well, how far are we actually branching? It's 1, 2, 3, 4, 5 instructions in the future. And if we look at our branch encoding, it already assumes PC plus 4 is kind of the default fall-through case. So that branch, as it's actually assembled here, should not have the label anymore for that branch L3. It should have the hard-coded number of instructions beyond PC plus 4 we're wanting to branch to. So that's 5 instructions in the future. That's PC plus 4, or the next instruction plus 4 more instructions. And we have the actual value of 4 encoded here directly in the branch itself. And that's the kind of math that you'll be doing yourself sort of manually. But the Mars assembler does show you what the exact equivalents are for that. Same with that earlier branch that was branching to L2, where L2 from this branch instruction is 1, 2, 3, 4, 5, 6, 7, 8 instructions in the future. And so consequently, we should have the value of 7 encoded directly into that branch target offset. And that's exactly what we have there. And this works for both branching forward as well as branching back. When you're branching to earlier instructions, what you'll see is a negative offset encoded in that 16-bit immediate. And that's exactly how we're going to have to implement it as well. Let's leave things here for today. Only major takeaways, definitely play around with exploring compilers. I'm not worried about you using it to cheat. If you understand how to use it well enough and you can use it to answer your homework questions in a way that is not obvious, that's perfectly fine. That means you do understand that connection pretty well. And then Mars can be very helpful in terms of understanding pseudo instructions as well as understanding branch target offsets. You just have to watch out for some of those foibles as you compare what GCC thinks valid MIPS assembly code and what Mars and consequently the class believes is the textbook MIPS assembly we are supporting. I'll leave things here for today. As always, let me know if you have any questions. Thanks.